Greetings everyone. This is actually a bit of a continuation on the previous video that I posted on the homeworks, and particularly on the homework on isomers. I want to make a couple of comments. One was that I made a silly mistake. Well, not a silly mistake. It's not a mistake, but I gave the wrong argument. I said the following. Remember, at some point I was considering this kind of isomer as a potential, right? I was thinking of this to be a potential hydrochloric, sorry, hydrocarbon, but this is not correct. This is not one. We saw that. For one thing, we said, oh, the number doesn't match, right? Because we had 10 hydrogens instead of the required 12. So that's why we dismissed it. But there's a much more pertinent reason to dismiss this. This is not a tree. And these things have to be trees. Again, I'm not a chemist. Chemists have no knowledge about chemistry, but apparently these have to be trees, and it is not a tree, because you see here we have a circuit, a cycle. And that's why the count is also off. And that's what I want to talk a little bit now about. How do we know that if you look at one of these possible hydrocarbons, that if you have n carbon, that necessarily you have to have 2n plus 2 hydrogen. I want to address that issue. Okay, so we have a couple information about, so let me, I'll erase this one again. So what is the information that we have? We know that this guy, so what is my question here? Okay, so let me say, if N, see how many H in one of these hydrocarbons. And the answer is 2n plus 2, but why? So we know that this is the answer, 2n plus 2, but why is that? And I want to address this because it is something that we can solve. And okay, it is a tree that we have. We know that these things are trees, so each of these are trees. However, they are not rooted trees. Okay, now if we want to do calculations, so we remember we have these nice formulas. Oh, I guess, sorry, that's not, I don't have them anymore, but let me write them up. What are our nice formulas? We have that the number of leaves plus the number of internal vertices. Well, it's either a leaf or an internal vertex. We had this, and then we also had, and this, but this was for a full emery tree, that n is equal to m times I plus 1. These are the two formulas that we use to calculate the number of vertices, leaves in internal. I do a review of this later on also again, but this requires, to talk about emery trees, to talk about leaves and internal vertices, you have to have a rooted tree. This is only for rooted trees. It makes only sense because that the notions leaf and emery and so all depend on a root. Okay, so if we want to use this formula, we have to turn these trees. We have here 3 possibles, and these are the 3 only ones that I didn't prove that, but that's what also, let's say, without proof we accept that they are the 3 only ones. Okay, now we're going to do this. So we're going to pick a root. Now we have to think a little bit of what should we take as a root, and it is a bit subtle. First of all, what do you think the leaves are going to be? Now let's think about a leaf. What is typical for a leaf is it has no children. So what is the degree of a leaf? 1. So that is unquestionable. And what has degree 1? Well, exactly all the hydrogen atoms. They have degree 1. So the H are going to be my leaves. Yes, true except if you pick one of the h as a root. Okay. Should I do that or should I not do that? So if I pick one of the h as a root, then all the other ones are leaves, and that kind of is a bit special. Now I want a full emery tree, because otherwise I cannot use the second formula. How far are we away from that? Well, definitely if I take h as to be a root, say, for instance, just simply think of this as here h is the root, and then just look at this in this direction, you can visualize the structure of the tree, right? So notice that this would be, this guy would have only one child, this guy would have one child, one, two, three child, 1, 2, 3 children. Remember, we're looking in that direction for seeing the children, right? Okay, if you don't, okay, you say, Professor, I don't see it. Okay, you don't see it, I'll make you see it. Here you go, and now we turn this around like this. Okay, now you, and so you see now that the root here, perhaps I should make this a bit bigger, right? So, somehow, oh, I guess I cannot do this anymore. Okay, anyways, yeah, it's a bit weird now to read it, but anyways, you see here, just looking at the picture, you see that this has, sorry, I didn't want to do that, that this has only one child, and then this has one child, 2 children, 3 children, and so on. So it is not a full emery tree, right, in this case, because the number of children should always be the same, except for the leaves. So that's not a good choice. So I'm not going to do that. So let me return this. So I'm not going to take a hydrogen atom as a root. So I'm going to take one of the C's as a root. Now, it is, again, a little bit subtle. Which C to use? Well, let's think about it. We see that there are cases where one of the C's, and perhaps many more, if I mean, this is for 5, right? But now we're doing this for general N. One of the C's has as children only, if we would make this the root, what would be the children? This guy, this guy, this guy, and this guy, right? So, okay. And then, but each of the other ones then, if you now look at this one, thinking of this as the root, how many children does this have? Remember, you cannot go that way, right, for children. You have to go now away from the root. So 1, 2, 3 children. Again, not full. I want to make a ternary tree, or perhaps a quartary, 4-array tree, or a 3-array tree, ternary tree. I'm still debating what to do. But if I pick this thing, it will be not working. However, that's the only thing that I should not do. And I know there are H's, right? It's going to be an isomer. It is going to be a hydrocarbon, so there has to be hydrogen, and those hydrogens have to be attached to a C. So there are going to be C's that have hydrogen atoms attached to them. Not all of them. You see, this is an example where there are no hydrogen atoms attached to the carbon. But most cases this happens. I mean, in fact, here it happens for all of them as well as for all of them. Okay, so I'm going to pick one of those, and it doesn't matter what one. So I'm to make that point, I'm going to take one a little bit out of this C here. Okay, now let's think how many children does that C have? Well, it's the root, and we know that the degree of C is 4, so it has 4 children. Because, see, what happens in a tree, right? In a tree, somewhere, if you're somewhere, one of the nodes in a tree, you have exactly one parent. What is this? I think, sorry, this froze. You have exactly, here you are. You have, so I forgot to write the parent. So I'm looking at this guy, right? Well, sorry, that's way too big. Okay, let me I'm talking about this guy. Let's not circle this one. So this one has one parent and then many children. Let's make extra children. So what is the degree? Is the number of children plus 1. So the degree is the number of children plus 1. Right? Because you also have a parent. Well, that's not true for the root. So the number of children for the root will be 1, 2, 3, 4. The number of children of all these other 3 guys will be 3. Because each of these C's See, carbon vertices will have a previous parent and has 3 more children. So everything has degree 3. Of course, the leaves have no. Everything has 3 children, except for the leaves. They don't have children, except for this guy, that root. So what I'm going to do now, and this is where I said it is a little bit tricky. This is a whole long story to say. I will remove one of the hydrogens. Okay, so I'm breaking my molecule. So let me get rid of this little guy here. Oh, that's why. Okay, let's get rid of this guy. I'm going to take this as my root. Okay, and I'm removing one of the hydrogens. So let me do that in red. So I'm removing this hydrogen. So remember, we have. I'm building now a tree with one less hydrogen. We have to keep that in mind at the end. And now I claim if I make this the root, I get a full ternary tree. And I can do this whichever I choose, as long as I choose a C that has at least one hydrogen, and there must be always many. What happens now? Every C has degree. This C, the root, has 3 children, because I removed one of its children. The other C's have parents, and therefore have 3 children, because their degree is 4. So every C has degree 3, has 3 children. Sorry, every C has 3 children in this tree, and these are the only, and the rest are leaves. So we are now, the choice I made, so I'm going to say here, so pick C with H attached, and make it root. Well, yeah, make this root. And remove this. So we pick a C with an H attached, at least one H. And then we do 2 things. We remove the H, and 2, remove that H vertex, and make C the root. Make that C the root. Okay, so I repeat, this is exactly what I did here, right? So I removed one H and make the C the root. And then the claim is what we have. Oh, what is that for a weird thing? What we have, I'll get back in black perhaps. What we have is a full ternary tree. Think about it a little bit more if you don't get it, but this is a full ternary tree. So now we can use our formulas here. So, okay, let's see. What is L? The number of leaves. That is the number of hydrogens. So this is the number of hydrogens in the isomer. Actually, -1, because we removed one of them. Okay? So this is what we want to find out. How many hydrogens are there? Okay, and L is going to be 1 less than that. Okay, so if we know L, we know also how much hydrogens there are. So what is I? These are the internal leaves, but we know exactly what they are. These are the carbons. This is the number of carbon, and by I'm saying this is N. Oh yeah, there are too many N's here. So let's say if there are K many carbon atoms, how many H atoms are there in this string? Okay, so we know that this, let's call it just I. Let's call this just I because that's what it is. Okay, sorry, the name of this variable here, it's better to kill this. If there are I many C's, and I in this case corresponds exactly to the internal ones, because the C's are the internal ones and nobody else is internal, because the H are leaves. The H are the leaves and the C's are the internal ones. It's very simple. Okay, so that we know. And so now we have our formula here. So we remember what we have is that these two quantities are equal. So we have, from this formula, we can get the formula L plus I is equal to Mi plus 1. Very often that's how we use the formula. So let's put everything together. L plus I, but I equals M. What is M here? So this means M is 3I plus 1. So L is equal to 2I plus 1. Right? Just solving this equation. Now, what is the number of hydrogen? Remember, it is 1 more. It is L plus 1. So it is 2I plus 2. And that's why we have this tells if there are I many C, there are going to be 2I plus 2 many H. And that is where this formula comes from. Now, I'm going to do a quiz on this, and so I'm going to do a review for that too, but I have this now, have set this up, so I want to do another review. I'm going to do here, let's see, the mad scientist. I'm going to be a mad scientist. And what I'm going to do is I'm going to make things that probably don't exist. I am absolutely ignorant when it comes to chemistry. So what I did find is, if I look it up, is that nitrogen, so nitrogen has valence, I don't know what you call it, valence 5. That means that if it bonds with hydrogen, it can take exactly 5 hydrogens. Or if it bonds with something, it has degree 5. So if for us this means the degree of hydrogen, nitrogen is 5. And remember, the degree of hydrogen is 1. That stays the same. I could have taken something else here. I could also take, forget now, what is the other one I could take? I had to Google all this because I have no idea what all these things are. I think, let me see. Where is it here? Chlorine. You could also take chlorine, apparently. What do I know? Okay. So I'm going to build a super scientist, a mad scientist molecule that is probably going to destroy the world. And this is going to be NiH. And that's the question. If I want to make a molecule with I many nitrogen, how many hydrogens should I use here? So I put a question mark. So it's the same question, but instead of carbon, I now, which has degree 4, I now do nitrogen. It has degree 5. Okay. So remember, let's look at a possible case. And there's a very simple one where we put them all together here. So these are the N's, the nitrogen. Okay, and they all gonna have bond 5. So that's they bond here together, and then so there's the outer ones. These are gonna have 4 more hydrogens attached to it, and the inner ones have 3 more hydrogens attached to it because they have now 2 nitrogens already. So remember, the degree has to be 5. And so here is my mad scientist formula. I'm 100% sure that this would blow up, or probably doesn't exist and probably doesn't work. I have no idea what it would be, but it's fun to think about it, right? So here are the H's, and here we have another 4 here. So of course we can count here. So in this case, I is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? And how many H? So the number, let me call this little H here, the number of hydrogens. How much is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is an N, right? Okay, yeah. Yeah, my N's and H's look really the same. No, that's really bad. Sorry, I lost 13, 16, 20. I find 20. So what's the formula? Okay, so let's do exactly the same as what we did before. So make a rooted tree. Okay, and we know that the leaves are going to be the H. Especially if I would take one of the hydrogens as a root, then that would not be a leaf. So I'm not doing that. So make a rooted tree so that all the leaves, all the H are leaves. In other words, make a rooted tree rooted at one of the nitrogens. But again, I want to do a nitrogen. For the same reason as before, I will have to remove one of the nitrogens from the root. So make a rooted tree by taking an N with a hydrogen which we then remove. That one hydrogen. There might be more hydrogens. We don't know. I mean, this is one combination, but there might be. I invite you to find more combinations here, even for 6 or for even for less. The question is just now, how many would there be? If it exists, how many? which we then remove. So we remove one of the H. So I'll do this again. I pick one at random. Let's pick this one here, somewhere in the middle perhaps. So I'm going to put this. This is going to be my root, but I am going to remove one of the H's. Why do I do this? Remember, look now. This, how many children does this guy have? 1, 2, 3, 4 children. How many children does this guy have? Now think. This is the parent relation here, right? So remember, making a root is basically putting an orientation and make it into a directed graph. Okay, so this is now how the directed graph works, right? So by taking this root, I have basically I took a center and everything promulgates from the center. Okay, so so looking at the next one here, for instance, what is the number of children that he has? Well, 1, 2, 3, 4, because its degree is 5 and it has one parent. Same here, same there. So all the n's, and this one too, and this one too, all the n's are internal, including the root, and have 4 children. That means we have a 4-array tree. So this is a when I remove the hydrogen, right? We get a 4-array tree, and I make one of the hydrogens the root. This is a 4-array tree. So this gives me a 4-array tree. Okay, so we have the formula. This is the formula I'm going to use in this form here. L plus I is mi plus 1. So L plus I is 4i plus 1. Now, we solve for L, that is 3i plus 1. Now remember, L is the number of leaves in this truncated molecule in which I took away one of the hydrogens. That probably makes it extremely unstable, so probably this was a major explosion in my laboratory. But now I have to put it back in there. And so that would mean that I have to add one more. So the number of hydrogens is one more than the number of leaves, so that is 3i plus 2. And that is the formula here. So we have NiH 3i plus 2. And does it fit the calculation here? If I is 6, then this should be 1820. And that's exactly what we have, right? Okay, so this shows you that that's where these formulas come from, by the way. If you might, I don't think it's explained neither in the book, but I just wanted to show you that you can, in principle, now play chemist, mad scientist. Okay, so please don't try this at home with actual nitrogen and hydrogen, because I think, as far as I know, they are not good friends, right? They are very volatile, gives volatile combinations. But anyways, so have fun.